Hi, kids. Mr. Dorfler here. Um, I was kind of going back and forth about whether or not I was going to make a video for this last part of section 4, but ultimately I decided to go ahead and do it because it's a challenge. Okay, this last part is a challenge. It's going to take what we've learned over really the entire last this chapter and combining them all into one scenario. Okay. Now, when we come to do work on this, I'm just going to challenge you to do a particular question. And I'll tell you what that is a little bit later on. There's my trickery there. But whatever problem I decide to give to you as challenge, I want you to work on it. And on Monday, or I guess that whenever the next day of the school week would be, I will take that question and I will work it out for you so you could see how to solve it. Okay. So it's going to be a challenge, but I know you can do it, and don't sweat it too much. Okay. All of this you've done at some point, but now we're really putting it all together like a final masterpiece. So let's go. This is talking about overcoming friction. Okay. There's no lead up into this question. There's no new material because, like I said, there's only going to be stuff that we have done. So we have a student that attaches a rope to a 20-kilogram box of books. Again, some of the scenarios that we come up with are just fantastic. Okay. I especially attribute it to the pictures that go along with it. I don't know why this individual doesn't have at least it's on like a roller, not a roller skate, like a skateboard or something like that, or a wagon. But instead, no, she decided to pull a box of books without wheels on a concrete path. To each their own. Anyway, he pulls with a force of 90 newtons at an angle of 30 degrees with the horizontal. The coefficient of kinetic friction between the box and the sidewalk is 0.500. We are tasked to find the acceleration of the box. We got a lot of stuff going on here. We got forces, we've got angles, we've got masses, we've got coefficients of kinetic friction, and we have to figure out what the acceleration of the box is. So let's get into it. Let's first list what we know. We know the mass is 20 kilograms. 1 second, please. I'm going to have to pause the video. Okay, I'm back. Sorry about that. I really hope this is working the way I wanted it to. Don't usually pause videos in the middle of it. It was my daughter who sent me repeated FaceTime messages only to tell me that her crested gecko had peed on her bed. All right, so I'll be real honest. I hope the audio wasn't recording when I was doing this interruption. Anyway, we have the coefficient of kinetic friction, the mu k, at 0.5, again, unitless. And we know that we have a force applied of 90 newtons at an angle of 30 degrees. So we have somewhat of a free body diagram listed like this. So this is going to have to be a multi-step process in order to solve this, okay? Because we only know so much, so we have to go through the litany, that's a fun word to say, of formulas that we've learned in this section or this chapter to help us solve all the way to acceleration of the box. So first thing is, let's set up a coordinate system and then determine the forces, the vectors of both the x and the y that's being applied to the box, okay? So we take the, if we look at this coordinate system here, we could create a 90-degree angle if we were to draw a connecting line here. So in order to find the force applied in the vertical or y direction, we take 90 newtons times the sine of 30, and we get 45.0 newtons. To get the x, or the horizontal direction, we take the F applied of 90 newtons times the cosine of 30. We've done that before to get 77.9 newtons to the right. All right. So now we're starting to get some values here, but we're just getting started. This is a three-part process. Okay. So we have to first go in this order, A, B, C. Just keep that in mind. Well, I guess this is kind of like your starting point here, finding the components. But then we get into A, B, and C. So part A, we're going to find the normal force, okay, by applying the condition of equilibrium in the vertical direction. Now remember, equilibrium is when all forces are basically equal, whether an object is at rest or in motion. Okay, if the object is in motion and not accelerating, then it's in equilibrium. Okay, there's essentially no net force in those scenarios. So we take the sum of all the vertical forces and set them equal to 0, which is representative of the net force. And in this summation of the or the vertical forces, normal force is in there. Okay, so we're going to expand this. Okay, let's see if I can get my pointer here. We're going to expand this out and to list all of the vertical forces. Once we have done that, we are then going to calculate the force of kinetic friction on the box. And so we're going to take that coefficient of kinetic friction equation, which involves the mu k and our newly calculated normal force from part A, to solve for Fk, because we have to use the Fk in our last part, part C, where we are going to apply Newton's second law along the horizontal to determine our acceleration. But instead of being the F equals ma, we have the summation of forces in the horizontal direction. And so that the kinetic friction that we're going to calculate in B is actually a horizontal force that's opposing the motion or the movement of the box. So a lot of the next few slides are going to look like a mess. But remember, when the problem that I assigned to you, it's going to follow the same procedure, okay? So don't sweat it. Just write these procedures down on a little paper, and you're going to be okay. So let's look at solving part A. Okay, I told you it's going to be a jumbled mess. Anyway, so to apply the condition of equilibrium in the vertical direction, you need to account for all the forces in the y direction. That is the gravitational force, Fg, the normal force, which we're going to be solving for, and the F applied that you calculated in the very start of this problem. Okay, so we are going to basically determine what the gravitational force is first, okay? We know what our applied force is. That's 45 newtons. We figured that out. But in order to find our gravitational force, our Fg, we have to take the mass that we were told in the very beginning and multiply it by the gravitational acceleration on Earth is 9.81 meters per second, and we get a gravitational force of 196 newtons. Okay, so going back to this setup here on the previous slide, the sum of all vertical forces is equal to 0 or equilibrium. They cancel each other out essentially. So we have the normal force plus the applied force and minus the gravitational force. Why is it minus? Why do you think so? Well, because gravitational force, they're vectors and it's downward. So that's why it gets the initial negative sign. And we set all of those equal to 0. So we can go ahead and plug in what we know. We know the F applied in the y direction, and we know our gravitational force. And so we put them in there. We don't know our normal force because that's what we're solving for. Plus 45 was our F applied, and minus 196 equal to 0. But just like any other algebraic equation, we can arrange this setup to solve for our unknown. And so we're going to subtract the 45 and add the 196. By doing so, that gives us our normal force of 151 newtons. Now again, the tip right here, as I was just kind of hinting at, remember to pay attention to the direction of the forces. Okay? Very important. So, we are done with part A. We have solved our normal force. On to part B, where we have to solve our kinetic friction. Okay? So, again, we're going to take that coefficient of kinetic friction that we saw earlier in this section, where it is going to be mu k is equal to Fk divided by normal force, rearranged to solve for Fk. So now I get mu k times Fn. So we were told in the beginning the coefficient of kinetic friction was 0.5, and we just solved for our normal force, which was 151, and this does have newtons, so our final answer for our kinetic friction will be 75.5 newtons. Okay, part B was actually pretty quick. Part C, now we use Newton's second law, where we use the summation of forces in the horizontal, set them equal to mass times acceleration, and then we're going to rearrange them, that formula, to solve for acceleration. So, going back to the very beginning calculation, where we found the applied force in the x direction, our component, and we subtract from that our kinetic friction. Again, I asked you, why do we subtract the force of kinetic friction? Because it goes back to what we talked about in this chapter. Friction acts in the opposite direction of the acceleration or of the motion. So it's going to be given the negative sign treatment. Okay? So we calculated 77.9 newtons of force applied in the x or horizontal direction. Subtract from that the friction, which is acting in the opposite direction, which is 75.5 newtons, and divide that by the mass of our crate. Sorry, I was thinking a couple steps ahead. And so when we do that, we remember that a newton is really just kilograms times meters per second squared in disguise. So if we kind of break down newtons, we can then see that we can cross off our kilograms, and we're left with the acceleration of the box of 0.12 meters per second squared to the right. Now again, you were not told in the problem itself the direction in which they are pulling it. But based off of the fact that we're not told that it's to the west or to the left or whatever, that we can always typically assume that any direction is going to be in the positive. Okay? So keep that in mind. That's why, even though it doesn't say it, that our final answer is going to have the label of to the right, because acceleration is a vector, so we got to provide a direction. And we made the assumption because we are awesome. So what I want you to do is on page 1, on page 141, practice E, okay? I want you to do number 1 on practice E, and that's it, okay? Again, this is just a challenge question for you. I want you to go to page 141, practice E, number 1. I'm not going to have you turn this in. I know I probably should, but I'm not going to. There will be a question that deals with this on the test, so I highly recommend that you do a practice on your own. Have your notes handy. Follow these steps, okay? Again, they're pretty consistent across the board here in terms of the steps you have to follow. Obviously, read the questions carefully in case you get something already provided to you. Maybe you have to add a calculation, okay? But just be careful. You're perfectly capable and qualified to do so. All right? So, again, page 141, practice E, Number 1, on Monday, I will be giving you the video on how to solve for that so you can see how well you did. Till then, I will see you all later. Bye-bye now.